Here is the solution to F6. I think F6 is a good example of a problem that looks sort of difficult, but really isn't as long as you know a couple of things. Problem 6 gives you two differential equations, one that involves the first derivative and one that involves the second derivative. They name the y variable in the differential equation, they call that f of x and say, okay, this is the function that we're going to be focusing on. And they give us, as you can see, 1 point on f, 1 point on the solution curve. So we've got a differential equation and an initial condition. Let's see what they ask. For part A, they ask for the equation of the line tangent to the graph of f at x equal 1. What do you need to write the equation of a line? You need a point and a slope. They gave us the point right here. And how are we going to find the slope? Well, here's an expression that always gives the slope so long as I know an x and a y, a point. So I know a point, I use that to find the slope. 1 point each for using the slope and for the equation of the line. Okay, part B, we've seen this now a couple of times, using a tangent line to approximate a function, and then they're going to follow up and ask, is this approximation too big or too small? So what we really need to do is figure out if we're looking at tangent lines. They also give us one other key piece of information here that's important. They say that f of x is greater than, f of x is greater than 0. All right, so here's our situation. We know that x is positive, because it's between 1 and 1.1. We know that y, which equals f of x, is positive. So looking at the differential equations, if x and y are both positive, that means the first derivative is positive on that interval. It turns out that's not important. What is really important is that with a positive x and a positive y, the second derivative is also positive. So if I have a positive second derivative, that means the function f is concave up. And this is what the picture looks like with a function. Now, I did draw this f as an increasing function, but everything I say also applies to a function that's decreasing as long as it is concave up. The big thing here is if a function is concave up, then the tangent line will lie below the function. Which means if I have the line tangent at x equal 1, and I want to use the line to approximate the function value, I want to approximate this y value by using that y value right there. You notice there's a little bit of error there, and I know, however, that because f is concave up, that the approximation will always be too small. So if I put 1.1 into the equation of the tangent line, I get 2.8, and I know that f of this actual function value on the curve, f of 1.1, is slightly bigger than 2.8. How did they say it? Since y equals f of x at x equal 1 lies below the curve, the approximation 2.8 is less than f of 1.1. Good. Part C, find the particular solution y equals f of x with the initial condition f of 1 equals 2. All right, so they give us a differential equation and an initial condition, and they ask us to find the particular solution. We know what to do. We need to separate the variables, integrate both sides, and then celebrate. Oops, I left the C off the word celebrate. That's a major mistake. You'll notice in the scoring guidelines that if you do not include a constant of integration, you're only eligible for 2 out of the 5 points. Don't forget that. Let's look at their solution. Here's the differential equation. Separating means getting all the y and dy stuff on one side, all the x and dx stuff on the other, while the dy and the dx are factors of their respective sides. So here they have it separated. They divide both sides by y to the third and sort of multiply, I'm using air quotes here, both sides by dx. You get this expression. They integrate. They kind of included these two steps in one step right here. Find the integral, make sure you put a c on one side. Solve, well, they're using the initial condition to find the value of c, and then they're solving this for y. Uh-oh, y is squared, so I have to take the square root of both sides. Remember, the solution to a differential equation is a function. This y, which is the same thing as f of x, that once we find it, that's the solution. That's what they're asking us for, that function. So y turns out to be squared here, so when you take the square root of both sides, you have to introduce a plus or minus. So now, which one do we use, the plus one or the minus one? For that, you look again at the initial condition. If f of 1 is equal to positive 2, well, if I put 1 in here, if I put 1 in here, there's only one way that that's going to equal positive 2, and that's if I use the positive solution, not the negative solution. So it is the positive one. By the way, this expression in the circle is the same thing as the square root of that expression. They just did a little bit of algebra. If you reported your solution as the positive square root of this expression right here, you would be absolutely 100% correct. All right, that is the solution to F6. You don't actually need this restriction right here. You get no points for it, so that's a little bit esoteric. That's everything. So a problem that the hardest part is starting it. Once again, here's a theme. If maybe A, you get nailed. You do A and you do it fine because it's asking for the slope of for the equation of a tangent line, and you know you just need a point and a slope. Maybe B, you don't understand this approximation thing. Don't give up, because part C you may totally be able to do even though you cannot do part B. So remember, even if you're stumped on a part of a problem, stick with it. That's it. Thank you.